This is pre-calculus area under a curve practice problems. And here we're going to look at number 2. So we want to approximate the area under the curve f of x is equal to 4 to the power of x. So this is the exponent and 4 is the base. For the region 3 is less than or equal to x is less than or equal to 6 using 4 left-hand endpoint rectangles. Okay, so this is what we want to find, the area underneath our function between the x-axis and our function from 3 to 6. All right, so step A, we always want to quickly sketch the function f of x. So we know f of x is equal to 4 to the power of x. We're given that right here. And if we're not sure what it looks like, we can just use our calculators to quickly sketch it. So y is equal to 4 to the power of x. And graph that. And we're going to get that, and it looks just like this. So sketching it, go ahead and sketch it, and looks like this. Right? All right. So that is the sketch. And we want to find the area under the curve between 3 and 6. Okay? So here is 1, 2, 3, 4, 5, 6. So we want to find the area from 3 to 6. So it's going to be hard to see this because this curve goes all the way up here. So let's go ahead and just draw it like this. It keeps going up. Okay, so we want to find this area under the curve. Right? Alright, so that's the sketch in part A. Part B, we want to go ahead and find the width. So this was our sketch. This is our x-axis and our y-axis. Part B, we want to find the width of each rectangle in this region, right? And we know that that's equal to b minus a over n. And we know b is where we're stopping the region, so that's 6, minus a is where we're starting. And n is the number of rectangles, and then we are given use 4 rectangles. So 6 minus 3 is 3 over 4. Plug that in your calculator, it's 0.75. 3 divided by 4 is 0.75. Right? So this is the width of each rectangle. Part C. Carefully draw the zoomed in sketch of the region we are looking at and label the coordinates where the rectangles touch the curve f of x. So part C, our function is f of x is equal to 4 to the x, and we want to look at the region 3 to 6. So let's go ahead and just say, well, this is 3 to 6. Right? This is what we want to look at. And we know that from 3 to 6, it's curving up really tally, right? It's going up way tall. But I don't have enough room, so I'm just going to kind of draw it like this. Okay. We know it's going up. It's kind of in this shape. We know it's really going like this up. But I'm going to draw it like this because that's the room we have. Okay, so then we're going to use 4 rectangles. So we want, this is the graph from 3 to 6 using 4 rectangles, 4 left rectangles. Okay, and each of the rectangles is going to have width of 0.75. So let's go ahead and write, well, if that's 3, 4, 5, there's going to be 3 units in between, so it's going to be 3, 4, 5, 6, right? And each rectangle is 0.75 units. So 3 to 3.75. I'm going to use a different color. So 3 to 3.75. Right? 1, 2, so around here. 3.75. Because you add that. That's going to be the first rectangle. It's going to touch the left hand height. So it's going to have, this is going to be the point touching our curve. Right? Our curve right here is f of x. That's our curve. Okay. 3.75, well, the next one is, the next x coordinate is going to be when we add 0.75 to that. So that's 4.5, right? We can even use our calculator and say, well, what's 3.75 plus 0.75? That's 4.5. So here at 4.5, we're going to have another rectangle, but its height is going to be determined by this left side, right? So there is the next rectangle, right? 4.5, we add 0.75 again, 0.75 to add that, we get 5.25. 5.25 is right around here, 5.25. And again, we're going to use the height from the left side, right, from over here. So that's the height of the rectangle. And finally, we're going to go all the way to 6. If we add 0.75 to 5.25, we get to 6. But the height of this rectangle is going to be here at the function's value at 5.25. All right. So let's find these coordinates. We know this x value here is 3. The y value is when we plug 3 into our function. So if we plug 3 here, we're going to get 4 cubed, right? So this is 4 cubed. The x value here at this point is 3.75. The y value is when we plug in the x value 3.75. So it's 4 to the power of 3.75. Okay, the next point we have that touches our curve is the x value is 4.5. The y value, you plug it in, we plug x to be 4.75, so it's 4 to the power of 4.5. We plug in x to be 4.5. And finally, the x value of this point is 5.25, and the y value, you plug in 5.25 to x, so it's 4 to the power of 5.25. Okay, so that is part C. We are carefully drawing the zoomed in region and labeling all the coordinates right here, right here, right here, right here. The 4 points that touch our curve. All right, so let's go on to part D. Part D, write the expression for A, which adds the areas of each rectangle. Do not compute. All right, so the area, again, of our function, we could write f, or I could write 4 to the x between 3 and 6 is approximately, right, it's not exact because we're not including all of these regions here, right, we're just including the rectangles. So the area of this rectangle here, we know is going to be the base of the rectangle. So the base we know is this length here. We know the base for each rectangle again is 0.75. That's the base of each rectangle. So it's 0.75 times the height. We know the height of this rectangle here, right, is when we plug in our function f of x to be x is equal to 3. So it's 4 to the third power. Right, so that is the area of this rectangle. The area of this rectangle then is the base, again, is 0.75. The base of every one of our rectangles is 0.75 times, this is times, and here the height we know is going to be, when we plug in x is 3.75, we get 4 to the 3.75 power is the height of that rectangle. This rectangle, again, the base is 0.75. The height we know is 4 to the 4.5. Right, we already did all these calculations. Finally, the last rectangle, we have 4 rectangles. The base again is 0.75. And the height we know is 4 to the power of 5.25. Okay, so that is writing the expression for the area in terms of all the rectangles. We're not going to compute this. We're not going to simplify this. We're just going to write this down like this. And because in part E, right, we're going to express A in sigma notation, and this one begins with k is equal to 5. So let's go ahead and write this in sigma notation. This should be to the x power. right? So that's going to equal to some sigma notation. We're going to start with k is equal to 0 because that's what the problem asks us to do. And well, what is the pattern we see in this series, right? Well, what stays the same is 0.75, right? So that stays here. Times 4 stays the same too, right? Times 4 to the power of something, because that something is what changes each time, right? And I already know when we stop. I don't need to go ahead and calculate this because I know that if this is term 0, then this is term 1, this is term 2, this is term 3. So we're going from 0 to 3 here. So the stop is 3 since we're starting at 0. So we just need to find this exponent here, right? And to do that, we notice that, of course, it's a linear series because the width of each rectangle is 0.75. So we're adding 0.75. So it's in the form of y equals mx plus b, right? Because it's linear series. But we have y is equal to m, we know is 0.75. X, we have the variable k plus b. So we need to find what is b. To find b, we can go ahead and say, well, at the starting point, at k is equal to 0, what is the exponent for the first term? So this in the linear series starts off as 3. So this expression 0.75 k plus b equals to 3, right? At k is the first term, our expression equals to 3. Okay, so we know k is 0, so 0.75 k is 0 times 0 plus b is equal to 3. 0 times 0.75 is 0, so b is equal to 3, right? So we know this is equal to, our linear series is 0.75 plus times k plus 3. So here in the exponent, we've got to write that. It's 0.75 k plus, not b now, 3. Okay? So here is our expression for all 4 rectangles being added using sigma notation. All right, and remember this, do we use left or right? Well, remember we said it, you can look at the picture, we're using left endpoint, right? Because the height of each rectangle is given from the left side. So this is left endpoint. So because part F, we basically want to go ahead and, I'm going to write part F over here. Part F, we want to go from left to right endpoint, right? Right endpoint rectangles. We still want to use 4. The instructions say give the representation of A. So A we know is our function f from 3 to 6. And now we want to use sigma notation, but we want to use 4 right endpoint rectangles, right? So it's so easy to go from left endpoint to right endpoint because remember we just add 1 to our starting and stopping points, our indices. So this is just going to be the same thing except we're starting at k equals to 1, right? Because 0 plus 1 is 1. 3 plus 1 is 4, so we're stopping at 4. And we're going to, and this stays the same, 0.75 times, right, 4 to the power of 0.75 k plus 3. Okay, once we get part E, it's easy to go to part F because the right endpoint, we just need to add 1, right? Right endpoint, add 1 to the index, to the start and stop index. And plural index is indices. Okay, so that's part F. Part G is asking us to given our left and right endpoint expressions, calculate the value of A accurately. So G is just saying to go ahead and calculate it. Well, we know the left and right endpoints, so we want to actually calculate it. And we know that the left endpoint rectangle here in the picture is going to be an underestimate, right? Because we're not adding up all of this area, so it's an underestimate, right? if we went with the right endpoint rectangles, which you do, then it's going to be this area, and this is going to give us an overestimate, right? Because now we're going to be going over the curve. Here's our curve. We're going to be going over each time. So a good middle point is going to be the average of the under and over estimate, or the average of the left endpoint and the right endpoint. So let's go ahead and write that. A good approximation, the area under our curve from 3 to 6. The best endpoint is just going to be the average of the left and right endpoint approximations, right? So let's go ahead and calculate these. Here in part E, we could calculate it using our calculator because we know we have the program, sum plus, right? Let's run it. Starting is k is 0, so we're going to x is 0, stopping at 3, and our expression is 0.75 times 4 to the power of, and make sure to put this all in parentheses, because if you don't, you're going to go, it's going to only make this the exponent 0.75k. So 0.75 instead of k, we use x plus 3, close the parentheses, okay? Okay, so this is approximately 1653, so 1,653.88 units squared, right? And if we use the right endpoint over here in part F, what would that give us? Let's run it again. This time we're starting at k is 1 or x is 1, stopping at 4, and our expression is 0.75 times 4 to the power of, don't forget to put in parentheses, 0.75 x plus 3. Okay, enter, and that's approximately 4,677.88 units squared. Okay, so that's the over approximation, and in part, let's get rid of our calculator for a second. And over here and in part E, this was the under approximation. So again, the best approximation we can then deduce is going to be the average of the under and over. So that's just adding the under is 1653.88, right? Copying from there. Plus the over 4677.88 and dividing that by 2. So that's going to be the average. So let's go ahead and do that. 1653.88 plus 4677.88. I'm going to put equals now, because if I divide that there by 2, it's just going to, if I put this over 2, it's just going to put the right number over 2. So now I'm going to divide that sum by 2, and it's going to give me the best approximation of the area is 3,165.88 units squared. Okay, I'm abbreviating units with UN, and that is the best approximation of the area given our left and right endpoint expressions. Okay, so that's as accurate as we can get right now. Unless we increase, again, we could increase the number of rectangles, but I think we get a pretty good approximation using the average of the under and over estimates. Okay, so this is ending our precalculus area under the curve practice number 2.